music.
In the name of Allah, the most gracious, the most merciful. Praise be to Allah, and peace and blessings be upon the messenger of Allah, our master Muhammad, and upon his family and all his companions. Now let me begin. O Lord, expand my chest for me, make my task easy for me, and untie the knot from my tongue so that they may understand my speech. In the previous episodes, we discussed differential protection, covering both low impedance and then high impedance. In this episode, we will start with a very important topic, which is the sensitivity and stability test for differential protection devices. So stay with us. Thank you. End of Renaissance and dawn of Renaissance and dawn. It is well known that electrical equipment and devices go through 4 essential stages of testing before and after they are put into service: type test, routine factory test, commissioning test, and maintenance test. The type test is required to demonstrate that the device, for example, meets the specifications mentioned in its manual, in addition to complying with the relevant global standards. This type test must ensure that the relay remains working properly even under abnormal operating conditions according to standard IEC 60255 or IEE C379SO. Et look, 1255 OITB T37 en même temps. The routine factory test ensures the relay is free from manufacturing defects. It's crucial to verify the protection system's correct installation. This phase starts after equipment installation and plan verification. It involves checking wiring connections. We then examine each equipment piece individually and test all together as a complete system. Before initial operation, it is essential to verify the correct installation of the protection system. This phase starts after the equipment is installed and the plan is verified. We check wiring connections within and between panels, a process known as commissioning. Each piece of equipment is examined individually, then tested together as a complete system. Periodic maintenance tests identify issues from equipment aging, allowing for preemptive corrective actions. Protection relays operate only during faults, so regular testing is crucial to detect issues early. Tests for electrical equipment are divided into 3 sections. This is known as commissioning. Periodic maintenance tests identify issues from equipment aging, allowing corrective actions before problems occur. Protection relays operate only during faults, so issues may go undetected until then. Regular testing discovers relay problems before faults. Tests for electrical equipment are divided into 3 sections: equipment testing, secondary tests, and primary tests. Secondary tests usually precede primary tests. For example, to test the current transformer, CT, first test the CT itself to ensure no issues, then perform the CT secondary injection test, followed by the CT primary injection test. Regular testing helps discover relay problems before fault. The first section is the testing of the equipment itself, the second section is the secondary tests for it, and the third section is the primary test for it. Usually, secondary tests are conducted before the primary test. For example, if you want to test the current transformer, CT, the first thing you need to do is test the CT itself to ensure there are no issues, using the test we mentioned earlier. Then you would perform the CT secondary injection test, followed by the CT primary injection test. Then we suspect the CT primary injection test. Likewise, when testing, first make sure that the relay itself is working properly, and according to the diagrams, then we make sure to test it, and finally we make sure to test it. And sensitivity test. Finally, we make sure to test the primary stability and sensitivity test. According to studies, approximately 30% of faulty operations of protection systems in the electrical system are caused by errors in the setting, configuration errors, or design problems. However, we cannot afford to gamble with such critical errors, and there is no room for mistakes in a national electricity grid. Therefore, it is essential to conduct tests and simulations that closely mimic real conditions as much as possible to minimize these errors before actual operations begin. The stability test, or commitment test, is conducted with all protections that rely on comparing the values between 2 ends, like or. The purpose of this test, make sure to verify the integrity of the connections and the programming of the relays before the equipment is put into service for the first time. This is done for the transformers, lines, and the bus bars on which differential protection is installed. The stability test simulates an external fault on this equipment and then ensures that the differential protection for this equipment remains stable during this external fault, meaning that the value of the differential current remains 0. The sensitivity test, or what is known as the sensitivity test, involves simulating an internal fault within the equipment's boundaries and then ensuring that the value of the differential current has increased. If the differential current exceeds the differential current setting, a trip signal should then be activated. Ensure differential protection operates only during internal faults, not external ones. To test transformers, calculate expected differential and bias current using relay manual equations. Conduct a three-phase short circuit on the transformer's low voltage winding outside the transformer for external fault scenarios. Stability and sensitivity tests for transformers are crucial. The first step is to perform calculations for the expected differential and bias current based on the equations derived from the manual at normal tap. Secondly, we conduct a three-phase short circuit on the transformer's low voltage winding outside transformer after differential protection CTs for external faults. If CT is inside switchgear, close incomer CB after rack-in, then close outgoing CB after rack-in. Temporarily bypass interlock to close earth switch for outgoing feeder, as interlock prevents closing if CB is rack-in. If earth switch cannot close after bypass, perform three-phase short circuit on outgoing feeder at cable side. Rack-in, close the breaker, bypass interlock to close. We temporarily bypass the interlock to close the earth switch for this outgoing feeder because the interlock will definitely prevent closing the earth switch if the circuit breaker is in the rack-in position. If you still can't close the earth switch for this outgoing feeder, even after bypassing it due to the interlock mechanism, we can perform a three-phase short circuit on the outgoing feeder at the cable side. The most important point at this stage is to ensure that all circuit breakers are closed and in the rack-in position. The third step is to apply three-phase voltage to the high voltage transformer before the CT for the differential protection. Before the 60 related to differential protection, this voltage can be either 400V or 380V, and it can be obtained from an external generator or by pulling a cable from the low voltage AC panels, also known as ACDP panels, through the MCCB. If you want to test using an external generator, you need to know the expected current output from the generator, which we calculated in the first point to choose a generator that has the appropriate capacity to provide this current without overheating. The fourth step is to ensure that we use a device to check before performing the test, so we can confirm that the wires were not reversed when connected and that everything is correct. As is known, this has a significant impact. So we need to connect and ensure that it is in the counterclockwise direction. Fifth, we need to ensure that any unused or open CT core is not in the path of the current we want to create, so we can set a condition on its secondary CT before starting the test. Now, we turn on the MCCP and then measure the current values at both ends of the transformer using the clamp meter. After that, we record these values and compare them with the values displayed on the relay. Then we read the values of the differential and bias current displayed on the relay and compare them with the calculated values we obtained in the first point. We must ensure that in the case of an external fault, the value of the differential current is 0, while value of the restraint current is according to the calculations from the first point. Completing the stability test, we do the sensitivity test, simulating a free-phase short circuit within the protection boundaries before the current transformer for differential protection for an internal fault. This is done by closing earth switch. In some places, instead of a real short circuit, we swap CT connections S1 and S2. This involves swapping CT connections after opening the link for each terminal block or setting a condition by inserting a test switch. We then read the differential and bias current values on the relay, ensuring the differential current increases for an internal fault. Swapping on City Alexandria between AS1 and AS2, this is done after opening the link for each CT terminal block. Read the values of the differential and bias current displayed on the relay. Compare these displayed values with the expected values obtained from the calculations we performed in the first point. Conduct the stability and sensitivity test. After testing differential protection, proceed to test restricted earth fault protection. We need to compare relay values. After stability, sensitivity tests, perform another stability test to ensure changes are removed. Then proceed to test restricted earth fault protection. This was done during the sensitivity test. After completing the tests for differential protection, stability, and sensitivity, we then proceed to test the restricted earth fault protection, stability, and sensitivity using one of three methods, either by creating an external earth fault through a short circuit on only one phase with the ground, coming from the transformer low voltage, winding outside the transformer, meaning after the protection for restricted earth fault. Restricted airflow. Keep the generator connected to three-phase voltage at 3%. Apply voltage or inject current to bypass transformer protection, applicable only with external CTs, not pushing CTs. For earth fault simulation, bypass the neutral grounding resistor to allow current return. BEBUS is working on the transfer. CTs and protections must be external, not pushing CTs. Simulate earth fault current by bypassing the neutral grounding resistor. Connect the return cable before the NGR to avoid bypass. Retest the other two phases for accurate measurements. Repeat the process at minimum and maximum tap positions. For a transformer with 21 taps, test at normal tap 11, minimum tap 1, and maximum tap 21. This is true if the return cable to the injector is limited to after this NGR, otherwise the injector will behave as if there is an open circuit. Alternatively, you can connect the return cable to the injector before this NGR if you want to avoid doing this bypass. We should also retest the other two phases to ensure accurate measurements for all phases. In the end, we repeat everything mentioned earlier at the minimum tap position and at the maximum tap position. If there is a 21 tap transformer, we conduct this test at the normal tap, which is tap number 11, at the minimum tap position, which is tap number 1, and at the maximum tap position, which is tap number 21. We must redo all calculations for each tap. We repeat everything mentioned earlier at the minimum tap position and at the maximum tap position. If there is a 21 tap transformer, we conduct this test at the normal tap, which is tap number 11, at the minimum tap position, which is tap number 1, and at the maximum tap position, which is tap number 21. We need to recalculate each tap because they differ. Test twice and end with. Test a fold-in and out of the zone and focus on end zone. Test restricted earth fault, then a first fold. 3 first fold once in the zone and once out of the zone, and we need to focus on the end zone. Test restricted earth fault. Fold. Phase fault test in out zone, end in end zone. Key, voltage on. We conduct a single phase fault test once in the zone and once out of the zone, and we must also conclude in the end zone. There's a very important point to discuss. We can apply voltage on the high voltage side and create a fault on the low voltage side, or we can apply voltage on the low voltage side and create a fault on the high voltage side. If the current resulting from applying voltage on the high voltage side is very low and the relay cannot detect it, then we should apply voltage from the low voltage side to provide a larger current that the relay can sense, and to test the trip signal in this case, if you want to apply voltage on the low voltage side and create a short circuit or fault on the high voltage side, we do this by applying the voltage through a closed outgoing feeder that is in service, alongside a closed and in-service incomer circuit breaker. We can also use all the high voltage earth switches located before and after the CTs to simulate both internal and external faults. It's important to warn against performing a short circuit on the same side where the voltage is being applied, whether simulating an internal or external fault, because this will create a high fault current that could trip the generator or the low voltage AC as a result. Additionally, the wires may burn out because they cannot handle such a high amount of current. So we always perform the short circuit on the opposite side or a different side from the source because the transformer's impedance will significantly reduce the fault current. One of the issues we encountered during the test was that the calculations were based on the assumption that the CT was installed on the line side, but we found that the CT was actually installed on the phase inside the delta, which made all the expected calculations incorrect. The line current equals 3 times the phase current. If the relay trips during an external fault but remains stable during an internal fault, it functions correctly. This may require adjusting the CT secondary polarity. If the relay doesn't operate for either fault, ensure there's primary side current and the relay reads it. If the relay reads correctly, activate the differential function. Ensure the relay current exceeds the setting to trip. You are hot blowers or through the software you agree. If the relay doesn't operate for internal or external faults, ensure current on primary side is red. Check differential function is activated if relay reads correctly. Relay current must exceed setting to trip. For high impedance, ensure grounding resistance isn't burnt. Jumper resistance when injecting current to avoid burning. Ensure current within resistor capacity. If relay trips on faults, verify function and conduct tests. Confirm trip due to differential protection. If the protection used is of the high impedance type, you need to ensure that the grounding resistance itself is not burnt out. Therefore, it is recommended that when injecting current, a jumper is temporarily placed across this resistance to facilitate its removal when taking readings. It's important to note that the current passing through this resistance should not exceed resistor's power capacity to avoid burning the resistor again. So, if during the test the relay issued a trip signal during the external fault and during the internal fault, then make sure the relay is functioning properly and conduct secondary stability and sensitivity tests on it again. If everything is fine, then confirm that the reason for the trip is due to the differential protection and not other protections being activated. Let's explain percentage impedance voltage for transformers with an example. What does it mean when a 60 MVA transformer converting 132 to 30.8 kV has a percentage impedance voltage of 25.1137%? X% shows the voltage drop. At full load, the voltage drop across the transformer's internal impedance is 25.137%. For a transformer rated at 132 to 30.8 kV, this equals 25.137% of 132 kV, or 33.17 kV at full load. The voltage at the secondary terminals drops by 25.137%. At full load, it will be 132 kV minus 33.17 kV, resulting in 98.82 kV. A 132.8 kV transformer drops 25.137%, resulting in 98.82 kV. 25.137 divided by 100 times 132 kV will equal 33.17 kV at full load. This means that the voltage at the secondary terminals will drop by 25.137% at full load, which means that when the full load current is flowing, it will be 132 kVs, minus 33.17 kVs, resulting in 98.82 kVs. My price is 98.1% and my positive is 98.1%. Volt. This means you can calculate the voltage drop using this ratio, neglecting R as X is much larger. However, if R cannot be neglected, use percent over X%. The second use of percentage impedance voltage is to calculate short circuit current at transformer terminals. Higher Z% means lower short circuit capacity on the other side. Short circuit current is rated current divided by Z%. At the terminals of the transformer, it is known that the higher the value of Z% for the transformer, the lower the short circuit capacity that arises on the other side. The value of short circuit current can be easily found by dividing the rated current by Z%. Regarding the percentage, so if the transformer is rated at 262 amps and the transformer is rated at 2510 amps, the expected value will equal 262 amps divided by 25.137 times 100, which will equal 1.042 kiloamps. If it equals 2510 amps, then the expected high voltage fault current will equal 262 amps divided by 100, which will equal kiloamps. On 100, it will be equal kiloampere. Low voltage fault current is 2510 amps divided by 25.137 to get 9.98 kiloamps. Impedance voltage aids short circuit test calculations showing voltage to pass rated current in a short circuit. Use 3.468 kV on the 30.8 kV side, calculated by 25.137 x 100 x 13.8 kV. The percentage impedance voltage value represents the voltage required to be applied to the high voltage or low voltage windings to pass the rated current through both windings when a short circuit is applied on the other side. Just like we performed a short circuit test on the high voltage transformer, we need to apply a voltage of 3.468 kV on the 30.8 kV side. This value was calculated by multiplying 25.137 by 100 and then by 13.8 kV. The voltage is 13.8 kV. Kilovolts with a global reference of 38 kilovolts. So when we apply this voltage to the low voltage side and create a short circuit on the high voltage side, we will have a high voltage rated current for the transformer equal to 262A and a low voltage rated current for the transformer equal to 2510A. Therefore, we benefit from this ratio to know the expected current value that will appear when applying a voltage of 400V based on the principle of Prot. If a transformer has a capacity of 2 megavolt amperes, you can choose any megavolt amperes among them for calculations. The transformer can operate, for example, at 50 megavolt amperes as a minimum power, and at the same time, it can work at 6 Torx 7. megavolt amperes as a maximum power. However, we must not forget to choose the appropriate percentage based on the selected capacity. If the Z percent for the transformer is 24.03% at a capacity of 50 megavolt amperes, what will this percentage be at a capacity of 67 megavolt amperes? Therefore, Z percent at 67 megavolt amperes will equal 24.03% multiplied by 67 megavolt amperes. At 50 megavolt amperes, it will equal 32.43%. Now we want to take a comprehensive practical example of testing the stability and sensitivity of a transformer with a capacity of 60 megavolt amperes, which steps down from 132 kilovolts to 33 kilovolts and has an impedance percentage of 7.88%. The high voltage side transforms from 400 to 1, while the low voltage side transforms from 2000 to 1. Calculate HV and LV currents. HV higher 60 MVA, 3, 132 kV, 262 ALV. The high voltage rated current is 60 MVA divided by 3 times 132 kV, about 262 A. The low voltage rated current is 60 MVA divided by 3 times 33 kV, about 1049 A. To calculate short circuit current with 400 V three-phase voltages, use 2 methods. First, find the voltage. On the high voltage side, giving the rated current on both transformer sides if there's a low voltage side short circuit. This voltage equals 132 kV times the short circuit impedance of 0.0788, resulting in 10.4 kVs. 113 kilovolts equals kilovolt is equal to 10.4 kilovolt. Therefore, we say that applying a voltage of 10.4 kilovolts on the high voltage side, while the low voltage side is shorted on the three-phase, will create a rated current on both sides of the transformer. If we apply a voltage of 400 volts, how much current will that generate? Therefore, the resulting current on the high voltage side of the transformer, when applying a three-phase voltage of 400 volts, will be 262 amperes, which is the rated current multiplied by 400 volts over 10.4 kilovolts, and it will be approximately 10 amperes. As for the current generated on the other side of the transformer, which is the low voltage side where the short circuit is, it will be 1049 amperes, multiplied by 400 volts over 10.4 kilovolts, which will equal approximately 40 amperes. The second method for calculating the short circuit current is by dividing the rated current, the Z impedance. So we take 2162A, which is the rated current on the high voltage side, and divide it by the Z impedance, which equals 0.0788. The result will be 3330A. 33 amperes. Therefore, we can say that the resulting current when applying three-phase voltages on the high voltage side will equal 3330 amperes, which is the short circuit current calculated earlier, multiplied by 400 volts over 132 kilovolts, resulting in approximately 10 amperes. As for the resulting current on the low voltage side, it will equal 330A, which is the short circuit current multiplied by 400 V over 33 kV, resulting in approximately 40A. Now we convert this primary current, which is 10A on the high voltage side and 40A on the low voltage side, to the city secondary side. So the 40 amperes on the low voltage side will be converted to the city secondary side. Therefore, the value of the high voltage current on the city secondary side will be 10 amperes over 400, which will equal approximately 0.0252 amperes. As for the low voltage current on the city secondary side, it will be 40 amperes over 2000, which will equal approximately 0.02018 amperes. 0 or 0 ohm amperes. High voltage 262A 400 of 0.656. Low voltage 1049A 2000A. Conviction factor is a high voltage rated current ratio of 262 amps over 400 and is equal to 6 times 5, 6. As for the low voltage correction factor, it is the low voltage rated current divided by the low voltage city ratio, which equals 1049A over 2000A, resulting in 0.525. Now we calculate the value of the current or the input current to the differential protection by dividing the city secondary current by this correction factor. Therefore, the current going to the differential protection from the high voltage side will equal 0.0252 divided by 0.656, which equals 0.0384. As for the current coming to the differential protection from the low voltage side, it will equal 0.020018 divided by 0.525, which also equals 0.0384. Dividing 25 equals. Also, Now we calculate the value of the differential current and the bias current, where the differential current is the high voltage pilot minus the low voltage pilot, while the bias current is the high voltage pilot plus the low voltage pilot, all divided by 2. When testing the stability, the value of the differential current will definitely equal 0, while the value of the bias current will equal 0.0384. In the sensitivity test, the value of the differential current will equal 0.0384, while the value of the bias current will be half of that, equaling 0.0192. This table shows the results of the test during the stability test at normal tab, which is 11, in the event of a three-phase fault outside the transformer boundaries. As you can see, we applied voltages on the high voltage side and created a short circuit on the low voltage side. This table represents the results of the sensitivity test in the case of a three-phase fault within the transformer boundaries on the low voltage side. This table shows the results of the stability test for the restricted air fault. Now notice that we applied single-phase voltages only, while the three-phase short circuit remains as it is on the low voltage side. This table represents the results of the sensitivity test for the restricted air fault, where we observed that we reversed the polarity on the neutral CT secondary only to simulate an internal fault. Here, notice that we applied single-phase voltages only, while the three-phase short circuit remains as it is on the low voltage side. This table represents the results of the sensitivity test for the restricted air fault, where we observed that we reversed the polarity on the neutral CT secondary only to simulate an internal fault. Inspiring. Whoa, the renaissance of a nation. For a transformer with 3 windings, start by testing stability with voltages on one side, then create an external fault. Induce an internal fault on the high voltage side, test stability between LV and TV windings, create an external fault on the TV side, and an internal fault. Finally, test all 3 windings stability, considering percentage impedance changes. We create an internal fault on the high voltage side to test sensitivity. And then we conduct a stability test between the LV winding and the TV winding, where we apply voltage on the low voltage side. After that, we create an external fault on the TV side to test stability. And then we create an internal fault on the TV side to test sensitivity. We conduct a stability test considering percentage impedance changes, often missing on the nameplate. Typically, percentage impedance is between HV-LV and LV-TV on the nameplate. Applying voltages on LV side, HV-TV impedance is parallel. Calculate reactance. Multiply first by second, divide by sum. And therefore, when applying voltages on the low voltage side, the total impedance for the HV and TV will be in parallel. Thus, we can calculate the equivalent reactance in the usual way, where we say the impedance value of the first multiplied by the second divided by the first plus the second. Sensitivity can be tested in this case by creating an internal fault on the TV side, then creating an internal fault on the HV side, and then creating an internal fault on both HV and TV. Similarly, when testing for stability and sensitivity for the districted air thought, it involves creating internal and external ground faults on the HV side and internal and external ground faults on the TV side. There is a detailed example from engineer Mohammed Irfan, may God bless him, explaining these cases in detail with the numbers, and we will include it in the attachments. Now, we will pose a new question, which represents the second part of this lecture. How do we conduct stability and sensitivity tests for the differential protection of the bus bar? The first step is to ensure that a short circuit is made on all unused city cores in this differential protection by creating a short circuit on their city secondary. It is also important to ensure that the city core for the discriminatic zone and the check zone are in service. Secondly, we inject a single-phase current through the primary card injection kit, like the Odin, for example. Did you mention it like the Odin, for example? On each of the 2 consecutive circuits, this means that the correct method for injecting current is to inject current between B1 and B2, then inject current between B2 and B3, and then inject current between B3 and B4, and so on. You should also ensure that you are injecting on the same phase in both buses, for example, injecting from the red face of B1 to the red face of B2, from the yellow to the yellow, and from the blue to the blue. Typically, current is injected through. During both setups, after the circuit breaker, the line or transformer is used to simulate an external fault, where one feeds current into the bus bar and the other returns the current to its source as if one of the circuits is supplying the other. This is known as, and usually current measurements are taken from the relay screen or through the Zera device or any device capable of measuring the current value along with the angle. It should be ensured that the value is very small. With a value, testing is done in three ways: differential protection, injecting current into secondary circuits, or returning current through the protection zone before the bus bar. The current is read from one circuit while the other cannot read it. For differential protection, inject current into a secondary circuit, return current to its source through the protection zone. Testing has two stages. First, gradually inject current to ensure pickup. Second, raise current to trigger. Isolate circuit output to prevent faults. Ensure the bus bar protection signal disconnects all connected breakers. Distribute breakers across bus bars. Connect all breakers on the same bus bar to ensure disconnection. Isolate the bus bar and re-inject current. Protection should not operate. Repeat the previous method. In two stages, first gradually inject current until a pickup occurs for protection. Then, raise the current until triggers. Usually, the circuit output is isolated to prevent faults on the secondary circuit. Ensure the bus bar protection signal disconnects all connected circuit breakers on the same bus bar without affecting others. Breakers should be distributed across both bus bars. Alternatively, connect all breakers on the same bus bar through the bus before the circuit breaker, ensuring disconnection at fault. Confirm that isolating the bus bar and re-injecting current doesn't trigger protection. Now perform the same method on remaining phases, recording and comparing results with expected outcomes. If it hasn't disconnected all the breakers that are not connected to it on the same bus bar, then the breakers should be distributed across both bus bars to ensure that. It's also possible to connect all the breakers on the same bus bar through the bus before the circuit breaker and ensure that all breakers are disconnected at the moment of the fault. We can confirm that when isolating the bus bar going to the circuit and re-injecting current again, the protection will not operate. Now we will perform the same method as before, but for the remaining phases, we record the results and compare them with the expected outcomes. Then we perform the retest again by connecting the disco connector to the other bus bar and repeating what was done previously on three phases. We also ensure in all previous cases safety of the circuits, disconnections, and the signals displayed on the relay, as well as the SCADA system or the SAS system. Translation mo kay Nasi Pangkar. Inspiring. The revival of a nation. This lecture covers line differential protection testing. Injecting currents from two locations with under 10 ms delay is key. The test ensures no trips during normal or external faults. How can we inject two currents from different locations, one from the north and the other from the south, over 100 kilometers apart, simultaneously with a time delay under 10 milliseconds? If the delay exceeds this, the protection system activates a trip signal. The test ensures no trip during normal operation or external faults. If a trip signal is issued when the line is energized, the system is incorrect. If stable with no trip, the system is correct, which is protection. But in this case, if no trip signal is issued, it is not ideal for protection tests. When energized, a trip signal shows an incorrect system state. Stability without a trip means the system is correct, known as protection. Engineers have sought solutions, and GPS technology helps in testing. When the line is first energized, a trip signal indicates an incorrect state, no signal, and stability means correct state. However, a fault might be misidentified due to incorrect state. Engineers sought solutions until GPS technology was found useful for testing. By placing devices at each end and using satellite communication, a stable time reference is created. Thus, fault simulation decisions rely on this synchronization. There might be a fault causing false detection. Engineers have sought solutions for these issues until scientists found GPS technology useful for testing. Synchronization ensures correct execution during a fault simulation. Both devices must synchronize time. Inject current at 0 moment. Devices at each end use satellites for communication and time reference. Fault simulation relies on synchronization. Time must sync for simultaneous current injection. Satellites see Earth as a point. GPS-based differential protection testing is standard in developed countries. Omicron offers a file with proper test procedures. This means that the time must be synchronized on both devices at each end, so that both devices inject the current at the 0 moment, as if the decision is coming from the satellites and not from the user. The satellite sees the Earth as a point, and thus it perceives the distance between the two ends of the line as returning to 0. It appears to the satellite that the current injection is sent to a single point rather than 2 points. Currently, the method of testing line differential stability using GPS is the standard approach in many developed countries. There is also a specific file from the company Omicron that outlines the correct procedures for conducting this test. We will include it in the attachments for those who want to delve into more details. For more information, you can also read this article, which is also included in the attachments, explaining the testing, the line differential stability scheme. For the 765 kilovolt transmission line, In South Africa, we have completed the final episode on differential protection. Key references include Dr. Mahmoud Al-Jilani's books, Dr. Ahmad Safi Al-Din's lectures, and works by engineer Samir Zamzam and Dr. Camelia Youssef, plus engineer Wasim Al-Dwaykat's book. Engineers in various fields, such as testing, protection, and design, have transferred their knowledge from years of experience to future engineers, allowing them to build on past work. This course is distinguished by essential references, including books by Dr. Mahmoud Al-Jilani and Dr. Ahmad Safi Al-Din, and works by the late engineer Samir Zamzam and Dr. Camelia Youssef. Also included is a book by engineer Wasim Al-Dwaykat. We acknowledge articles and lectures by engineers like Amjad Marmash, Abu Suhaib, and Hani Kamal, and others like Mohammed Rashad and Ismail Mohammed. For foreign references, we heavily relied on. This is his YouTube page, along with the books of the late engineer Samir Zamzam, books of Dr. Camelia Youssef, and the book by engineer Wasim Al-Dwaykat. May God reward them all with goodness. We cannot overlook the articles and lectures of distinguished and diligent engineers in this field, whom I advise you to follow, such as engineer Amjad Marmash, known as Abu Suhaib, and engineer Hani Kamal. And here are their LinkedIn pages, along with distinguished engineers like engineer Mohammed Rashad and engineer Ismail Mohammed. These are their LinkedIn pages as well, and many other distinguished engineers. May God reward them all with goodness. As for the foreign references that have been heavily relied upon, they are, and the differential protection for Ziegler in the United States, the differential protection for Ziegler in, additionally, Alstom previously, which has now become part of GE, along with the famous book on testing, and also the book, in addition to Alstom formerly, which has now become with GE, in addition to the famous book on the test of the, in addition to the book to engineer Omar Atwa, we must thank the professional editor, Mr. Ahmad Al-Hayajne, for his work. And we extend our gratitude, appreciation, and respect to him. I can never forget to express my gratitude and appreciation to my dear wife who contributed to filming this entire course from A to Z, as well as to my beloved children, Noor and Kanam, who were patient with us until we finished filming these episodes completely. What has been successful is solely from God, and what has been wrong, careless, or forgotten is from the devil. Peace be upon you and God's mercy and blessings. Glory be to you, O Allah, and praise be to you. We bear witness that there is no deity but you. We seek your forgiveness and turn to you in repentance.